This research paper proposes a novel diffusion-based approach for low-light image enhancement, dubbed DiffLL, which leverages the generative power of diffusion models to produce results with satisfactory perceptual fidelity. The authors address the limitations of traditional diffusion models, which suffer from excessive computational resource consumption, instability, and chaotic content generation. The proposed method, Wavelet-based Conditional Diffusion Model, WCDM, utilizes the strengths of wavelet transformation to accelerate inference and reduce computational resource usage. By converting the low-light image into the wavelet domain using 2D discrete wavelet transformations, the spatial dimension is significantly reduced, resulting in an average coefficient representing global information and high-frequency coefficients representing sparse details. The WCDM performs diffusion operations on the average coefficient, reducing computational resource consumption and inference time. The model is trained with both forward diffusion and denoising processes, enabling stable sampling during inference and preventing content diversity. A high-frequency restoration module, HFRM, is also designed to reconstruct local details by utilizing vertical and horizontal information to complement diagonal details. Experimental results demonstrate that the proposed method outperforms existing state-of-the-art methods, both quantitatively and visually. As shown in Fig. 1, the method properly improves global contrast and presents vivid colors without introducing chaotic content. Fig. 2a illustrates the significant speedup of the proposed method, achieving a speed over 70 times faster than previous diffusion-based methods. Perceptual scores in Fig. 2b also indicate that the method generates images with better visual quality. The authors argue that their approach is more robust and efficient than existing diffusion-based methods, making it a promising solution for low-light image enhancement tasks. The application of the method to low-light face detection also reveals its latent practical values. This research paper proposes a novel wavelet-based diffusion model for low-light image enhancement, dubbed DiffLL. The authors highlight the limitations of existing methods, including histogram equalization and Rednex-based approaches, and diffusion-based methods, which often suffer from high computational resource consumption and inference time. To address these issues, the proposed approach combines the strengths of wavelet transformation and diffusion models to achieve efficient and robust low-light image restoration. The authors provide an extensive review of related work in low-light image enhancement and diffusion-based image restoration. They discuss traditional methods, such as histogram equalization and Rednex theory, as well as learning-based approaches, including deep encoder-decoder networks and generative adverse networks. They also review diffusion-based generative models, which have shown promising results in image restoration tasks like super-resolution, inpainting, and deblurring. The proposed DiffLL method leverages the generative ability of diffusion models and the strengths of wavelet transformation to achieve visually satisfactory image restoration and improve efficiency. The approach involves converting the low-light image into the wavelet domain using 2D discrete wavelet transformation, followed by diffusion operations on the average coefficient to restore the image. The high-frequency coefficients are reconstructed through a high-frequency restoration module, HFRM, to facilitate local details reconstruction. The authors detail the wavelet-based conditional diffusion model, WCDM, which forms the core of their approach. They explain the training and inference strategies, including the forward diffusion process and denoising process. The use of wavelet transformation allows for a significant reduction in spatial dimension, resulting in improved efficiency and reduced computational resource consumption. The proposed method is evaluated on publicly available datasets, demonstrating state-of-the-art performance in terms of both distortion metrics and perceptual quality. The authors also highlight the potential practical values of their method, including its application in low-light face detection. Overall, the paper presents a novel and efficient approach to low-light image enhancement, combining the strengths of wavelet transformation and diffusion models. The authors propose a wavelet-based conditional diffusion model, WCDM, for low-light image enhancement. The conventional diffusion model has two limitations. It requires a large time step and small variance, leading to costly inference time and computational resources consumption, and the reverse process may result in content inconsistency. The WCDM addresses these issues by converting the input low-light image into the wavelet domain and performing the diffusion process on the average coefficient, reducing the spatial dimension for efficient restoration. The model also adopts both forward diffusion and denoising processes in the training phase, ensuring stable sampling during inference. The training approach of the WCDM is summarized in Algorithm 1, which involves optimizing a noise estimator network via a loss function that combines the diffusion objective function and a content loss function. The denoising process is performed using a sampled noise with a conditioned input, resulting in a restored coefficient. The content consistency is realized by minimizing the L2 distance between the restored coefficient and the reference coefficient. The authors also propose a high-frequency restoration module, HFRM, to reconstruct the high-frequency coefficients of the low-light image. The HFRM utilizes depthwise separable convolutions, cross-attention layers, and progressive dilation res blocks to extract features and restore the coefficients. The restored average coefficient and high-frequency coefficients are converted into the output image using the 2D inverse discrete wavelet transformation. The network is trained using a combination of loss functions, including the diffusion objective function, detail preserve loss, and content loss. The experimental results demonstrate the effectiveness of the proposed method on various datasets, including LoLV1, LoLV2 Real, LSRW, and UHDLL. The method achieves state-of-the-art performance in low-light image enhancement, with improved efficiency and stability. The proposed wavelet-based diffusion model, DiffLL, is evaluated on 3 different datasets LoLV1, LoLV2 Real, and LSRW and compared with several state-of-the-art methods. Quantitative evaluations show that DiffLL achieves the highest PSNR and SSIM scores across all datasets, indicating superior image quality restoration. Additionally, it yields the lowest LPIPS and FID scores, demonstrating better visual quality. In terms of efficiency, DiffLL offers a moderate trade-off between performance and computational resources, requiring less time and memory compared to other diffusion-based restoration approaches. On the UHDLL test set, DiffLL outperforms all comparison methods in both distortion and perceptual metrics, showcasing its generalization ability for high-resolution low-light image enhancement. Furthermore, when compared to competitive methods on 5 unpaired datasets, DiffLL achieves the lowest NIQE, BRISC, and PI scores, proving its better generalization ability to unseen real-world scenes. Qualitative comparisons also demonstrate the effectiveness of DiffLL in enhancing image contrast and reducing noise, while other methods often result in underexposed, overexposed, or noisy images. The research paper discusses the enhancement of low-light images using wavelet-based diffusion models. It presents a quantitative comparison of various methods on different datasets, including DICM, MEF, LIME, NPE, and VV. The results highlight the superiority of the proposed method in terms of global and local contrast, detail reconstruction, and noise suppression. The visual comparisons on the UHDLL test set and unpaired datasets demonstrate the effectiveness of the method in improving image quality, avoiding artifacts, and generalizing well to unseen scenes. The method outperforms existing techniques in terms of visual quality, particularly in areas of exposure, color distortion, and noise amplification. The supplementary material provides additional qualitative results for further evaluation. The research paper discusses the enhancement of low-light images using wavelet-based diffusion models. It investigates the impact of LLIE methods on face detection tasks under weakly illuminated conditions. The authors propose a novel method that achieves superior performance in the high recall area and improves average precision from 26.4% to 38.5%. An ablation study on the wavelet transformation scale and sampling step demonstrates the trade-off between performance and efficiency. The paper also explores the effectiveness of the high-frequency restoration module and loss function terms, including diffusion loss, content loss, and detail preserve loss. The training strategy is discussed, which incorporates denoising in both training and inference phases to achieve consistency. The results show that the proposed method outperforms state-of-the-art methods and mitigates content diversity. The paper concludes by highlighting the limitations of the method, specifically its performance in extremely low-light conditions. This research paper presents a comprehensive review of various image and video processing techniques, focusing on low-light image enhancement, image restoration, and super resolution. The paper discusses the challenges in enhancing low-light images, including information loss and limited generalization capabilities. It highlights the importance of leveraging wavelet-based conditional diffusion models to achieve robust and efficient low-light image enhancement. The authors emphasize the significance of the proposed DiffLL model, which utilizes a wavelet-based conditional diffusion model to produce visually satisfactory results while reducing inference time and computational resource consumption. They also introduce a high-frequency restoration module to complement the diagonal details with vertical and horizontal information for better fine-grained details reconstruction. Moreover, the paper provides an extensive overview of the literature on low-light image enhancement, including the use of deep learning models, wavelet transformation, and diffusion models. It also discusses the limitations of existing methods, such as the inability to generalize to unseen tasks and the lack of real-time applicability. The paper further discusses the importance of the proposed method in enhancing low-light images for various applications, including face detection, image segmentation, and video restoration. It highlights the potential of the proposed model in enhancing the quality of images captured in low-light conditions, which can significantly improve the performance of downstream tasks like object detection and segmentation. The authors also discuss the future work in this area, including extending the proposed method to real-time video enhancement and investigating its effectiveness for other image restoration tasks. The paper concludes by emphasizing the potential of the proposed method in bridging the gap between complex research papers and concise, informative summaries for expert audiences.